If we were still in 18th century, that's how we would think about chaos. But we are actually in third millennium, so let's think about it like in 20th century, which is what we learned in 20th century is that the stage on which everything happens is space-time, which is woven into each other. It's not Newtonian space-time where, there's a clock and there's a floor, this room, that's our space. And the two are just divorced. So the way people think in field theory and statistical mechanics, they think about not in time evolution. That doesn't make any sense because, space-time can be rotated by Minkowski. The modern way of thinking is, and that unifies quantum field theory, statistical mechanics, chaos, and all kinds of other things, is not think of I'm here and I'll just march and I'll try to figure out what happens. We think in terms of what I would call book of life. What are all possible outcomes? To describe a system, I have to tell all possible things that can happen, number one. And number two, I have to tell how likely is a possible outcome. So, I can tell you there is a tornado, there is hurricane, etc. But then I have to tell you, probability that this will happen. And I have to compute this from my equations of motions. So that gives you a more modern sense of thinking of chaos, which you will see only in this course and no other, because it's certainly not in a Strogatz book. And that's called lattice formulation. So what we do is instead of thinking of stepping forward in time, this is, today, tomorrow, and this is what will happen to me, I take a temporal lattice, meaning I take all possible values of time from minus infinity to plus infinity. And Bernoulli law on that lattice says that when I compare my field, how tall am I on lattice side, 7 to how tall am I on lattice side 8, I have to satisfy the marching order, which says that the difference in the height between this multiplied by s times the next thing, that's just same equation with this thing written on the left-hand side, should be an integer. Suddenly, that's a big, strong constraint. Phi is a real number. This is a real number. But there's a unique solution to this condition. There's only one phi that will satisfy it, and it must be in a unit interval because I'm not allowed to stand out of the crowd. I must be between 0 and 1. So this is, where we call this integers time, or we call them anything we want to, it's totally different. Mathematical, this is just one-dimensional lattice, kind of thing that we have studied the whole semester when we were looking at discrete Fourier transforms. And on each side, there is a blade of grass called field. And, a lawnmower came by, so it's at most 1 inch tall or whatever. But it could be dead. It could be anything in between. That's what the field is. On each lattice side, I have to also tell you that there is an m. And that's an integer. And now we describe our system on a computer by finite block. The values of field, I'll call it lattice state. That's what the field looks like globally. And each site has a little block. And let me see, do I explain what happens next? Yeah, here is the picture. How do you think about it? So here is time, or lattice size, 0, 1, 2, 3, 4, 5. At every lattice site, there is a whole little world. There is a field that can take values between 0 and 1. That's what phi is. And it's subdivided in little regions which obey different law because I'm taking this modular thing. So I have to subtract integers. So now I'll walk through Bernoullistan, which is an infinite chain. On each one, I have a bunch of hill slopes and, precipitous falls. And I will say, well, as time goes, or as the lattices, I will give you marching order, which is, I'll tell you where to be at given time. These are the M's. And you will have to tell me exactly what the value of phi is at every step. And it always has to be within unit interval. So if I look at all of them together in n steps, this is a hypercube in which, in one axis, first time, another axis, I have a point. This is just a point in a large dimensional space. So that's Bernoullistan. To survive in Bernoullistan, you have to think globally, but you have to act locally. So, you have your 5-year plan. You want to go someplace. That's your global thinking. But at every particular step, law is the law and you have to satisfy it. So at every step, you have this condition and you have your marching order, what you're supposed to do the time step. So you have to satisfy this locally at every step. And that you can enforce by global equations saying, I take the total lattice, all the states in the field. That's this phi, remember? It was that thing down here. These are my marching orders, M's. And I can write this as a matrix equation saying, I compare the field to the field one step back. How do I do this? There's a matrix, which you've seen so many times. It's a shift matrix that says if I multiply this by that matrix, I will be comparing to one step back in the past. And then I have to stretch that by my stretching factor S. And that thing has to be the array of integer, my marking orders of n steps. And this is comparing the neighbors. And I'll give it a fancy name. So finding out what fixed point in n-dimensional space I have to have, because this is n-dimensional vector, I have to satisfy the equation that I take the unit cube in n dimensions, I multiply it by this matrix, which I'll call Hill matrix, honoring an American astronomer in 1880s. And the result of that has to be an integer, which is given, or sequence of integers. So there is a matrix, and now we do a Feynman trick. We put everybody on the same side. We call it a function of phi, and require that the law is that this function is 0. Now here it's rather simple because the function is linear, but the method I explain is true also for nonlinear conditions, not just linear ones. And now we have a law that this has to satisfy the global lattice state. So the blades of the grass on the entire chain are now thought of as a single fixed point in n-dimensional unit cube. And for every set of marching order, I'll have a different point in this unit cube. So I have to locally satisfy, that's my tangent space, as I keep saying, I have to satisfy my law, but I have to enumerate all possibility globally, and that would mean that I have understood Bernoulli system or any system at all. So usually the way you solve this problem, it's called the Newton method, which I'll not explain, but you have seen it. It says that if I perturb a little bit this function and I get something that's not 0 on the right-hand side, I can improve my values of phi by varying them in such a way that I have the smaller error next time. And to do this, I have to compute this derivative. Now, right now, it's n different points. So this is n times n matrix. But, if this is a continuous trajectory in space-time and I discretize it, this can be a very large matrix. And that's a Hill matrix. It has to do with the stability of a solution. And this has two, it has kind of obvious interpretation and then one that's not at all obvious. So my colleagues have given it a name. There's a fundamental fact that you have to understand about the Hill matrix. So what's a fundamental fact? I'll first say it in words, and people who understand sequentially will understand it. Then I'll draw a picture for people who are visual. So we have to satisfy a fixed point condition. So let's read off what this equation says. I start with a point and unit hypercube. In other words, I start with n values of the field, all of them between 0 and 1. Then I hit it by Hill matrix. What's a Hill matrix? Here is an example. It's something that has unity on the diagonal minus this number s of diagonal multiplying the unity. So it's a banded matrix, kind of things that you've seen whenever you do Fourier transforms. And now a miraculous thing has to happen. A bunch of real numbers multiplied by an integer matrix have to be converted into an integer because these are integer on every side between 0 and, let's say 5. And that has to add up to 0. So what it means is that I was looking for a condition for point that doesn't move. I was finding a fixed point condition. But now that periodic point has to be mapped into integer. So it has to have an integer value. And then I subtract an integer from it to translate into the origin. And that means that the total number of possible solutions is that this thing, gets stretched, hypercube gets stretched into something bigger. It's going to be called fundamental parallelepiped. And this fundamental parallelepiped has points which are on integer lattice because this combination has to be an integer. So the number of possible solutions of my Bernoulli law is actually the number of integer lattice points in fundamental parallelepiped. And the volume of this parallelepiped, which is determinant of the Hill matrix, actually counts the number of solutions. So this is not obvious at all. It's a fundamental fact. And I'll now draw it as a picture. So we start, if we have a period 2 lattice, so we just, after every 2 periods, we repeat, then we have only 2 fields which always repeat. And, one of those fields, let's call it phi 0, phi 1, are the 2 fields. The values that I'm allowed to have are within the unit square because unit hypercube in 2 dimensions is just a square. Now, this Jacobian matrix, it's something that has ones on a diagonal multiplied, and then it has this minus s's over, but we have taken s to just be stretching by factor of 2. So what happens is that corners of this hypercube, these are these 2 unit vectors, they get mapped by this matrix into something bigger, and the square gets mapped into parallelepiped. And lo and behold, the volume of this parallelepiped is 3. I've indicated the 3 unit volumes. These are called quadrilaterals. So the volume is 3, but when I count periodic points, there's 1 here at the origin. There is one here and one here. So there are 3 periodic points, 3 periodic solutions. And then because this is stalling the space, this doesn't count because modulo 1, that's the same point. So they're not 4 of them, they're 3. And that's what this law means, you know. We are being alerted by Atlanta. So that's a fundamental fact. It's really cute, surprising, but that's what it is. I can still draw this in 3 dimensions using mathematical or everything. In that case, you have a unit hypercube. It gets, stretched into fundamental parallelepiped, and you can verify that number of the points in that periodic points is the volume. But this is not true for any dimensions when you cannot visualize, and there is a whole subject of mathematics called, and also cryptology and computer science, which is studying these integer lattices and the volumes on them. So this is the mathematical fact. The second meaning of the Hill matrix is the one that kind of makes sense when you're doing calculation. But this matrix says that if I have a solution, so, moon, that's what Hill did originally, is moving around the Earth under influence of sun, and you neglect everybody else. So it's a 3-body system. And if I move it by a millimeter, every place along its trajectory randomly a little bit, then the solution will be changed. I will not close where I'm supposed to close because I'll be locally violating my Newton laws, or in Lagrangian formulation. Lagrangian does it globally. And, this measures the perturbation of the whole orbit. So you have a whole field and you got your blades of grass slightly maladjusted, and you're trying to get the right answer back. That's called Newton method. So what this matrix does, it propagates initial perturbation around. And then there's the fact that I cannot derive this class. It requires slightly longer course than 1 lecture on chaos, which is totally crazy. So the determinant of Hill matrix, this is a big matrix. It's a whole state on a lattice of all pieces of grass. Determinant of this matrix equals, this is a huge determinant, equals my original determinant, meaning if I start with slightly different points here and I compute the effect as it accumulates of the distance between them, they'll give me a temporal Jacobian. And Hill formula says that determinant of, let's say, 2 by 2 matrix, if there are 2 degrees of freedom, 3 by 3 if I'm looking at Lorentz, that Adler wants me to look at. But this is a 3 by 3 matrix, but it propagates long time forward and future. And I have a fixed point condition. I have to come back. So that's why this 1 shows up here. And it turns out that this huge matrix, in the limit of infinitesimal small time set, it's current, can be described in terms of small matrix whose side doesn't change at all as we go up there. And this was so remarkable. Hill just did it because he was a brave astronomer. What he did is he used, like we always do, if you have a periodic solution, you do Fourier modes. And he kept some number of Fourier modes. So this matrix was the number of Fourier modes he kept. It was only 3. But Poincaré thought about it, says, same. If I do this correctly, there are infinitely many dimensions and obviously different dimension. And how can this be true? So the formula, this relation is called Hill-Poincaré because Poincaré actually proved that this functional determinant can be related in this way. So now there is a tradition in dynamical systems, applied math, to think in time. So people compute the right-hand side. And nobody thinks globally. Everybody thinks locally, and there's a fundamental problem with it. And fundamental problem with it is that here, if you really try to do it honestly, here, whenever you have a small error in this matrix or in your calculation, as you keep applying your time evolution, it'll explode exponentially. So the right-hand side is actually uncomputable. It's a secret. We don't tell you that. We say, well, you can compute it for a number of steps, and that number of steps is called the pool of time. But you actually cause a problem. Whereas this is there's no problem computing the left side, even though it's very huge. This is a modern way of thinking of a problem that you learn only mathematical method course because Strogatz doesn't know that. Not that he even doesn't tell you that in this elementary book on chaos, but doesn't even know that this exists.